All right, hope everybody's doing well. Hope your families are healthy. This is the first half of the Thermochem notes. It's chapter 16 if you're in the online book, so you know. Thermo, what's thermo mean? Heat. And so this is heat chemistry. We're talking about the heat involved in chemical reactions. I don't know a chemical reaction that doesn't have any exchange of heat energy. And so thermochemistry is involved in every chemical reaction. So here we go. It's the study of the transfer of energy as heat that accompanies the chemical reactions. Anytime you have a chemical reaction or a physical change, you've got some kind of heat exchanged. Usually we measure this heat in a calorimeter. So calories, the calories that you intake as food is a measurement of energy. It's how much energy that food is providing you with. And so we're gonna talk calories some. Well, you'll see joules some in this chapter. There are 4.18 joules are equal to 1 calorie. So there's our conversion for us. So if you look on something that has ingredients in Spanish, I know the HEB Coca-Colas have ingredients in Spanish, and so they'll tell you the amount of kilojoules there, and then they'll tell you the amount of calories. A little secret for you, your food here, when it says 1 calorie, they capitalize the calorie on your food. They capitalize that calorie on the food because that's actually a kilocalorie. So 1 calorie isn't 4.18 joules. 1 calorie is 1,000 of these calories. You're talking about 4,000 joules of energy that is providing. It's a little way they can avoid writing kilocalories on packages. They just put calories capitalized. So we use a calorimeter to measure this energy. So a calorimeter looks like this. It's a box, and by the way, my drawing will look way better than the drawing in the textbook. But it's a box, and then inside that box there's another box, and inside that box there is some kind of container where you're holding stuff, some kind of bowl. And there's stuff in the bowl, and so what they're doing is they run leads. They run wires to that bowl. They have a thermometer inside of that outer box. That outer box is usually filled with water, so there's some water in the box on the outside. They usually have a fan somewhere that is pushing that water all around to circulate the water. And what they do is they cause that food to react, or whatever that happens to be in the bowl. They cause that thing to react, and when they cause it to react, it either heats up the water or lowers the temperature of water, and we measure the corresponding change in temperature. So that's what that's kind of what a calorimeter looks like. That's what a calorimeter looks like. So that's how they measure the calories on something. They can put your Cheetos in there, and they'll cook them, right, and see how much energy, how much heat is given off by that particular food. Whether it's Cheetos or not is debatable, but delicious. So when we measure temperature is, let's see if that'll focus for us. Focus. Temperature is the average kinetic energy of particles. All that it is, it's a measure of speed of particles. That's what temperature is. So we have to have changes in temperature to measure heat. So in Thermochem, we will use Celsius or Kelvin because it's changes in temperature. The difference between 25 and 30 Celsius is the same as the difference between 25 and 30 Kelvin. That Celsius looks like it needs a spell check on it. But there's change is the same. So in gas laws, we had to turn everything to Kelvin. Here in Thermochem, Celsius or Kelvin, either one will work. As long as they're the same unit. You can't have, I measured it initially in Celsius, and then I measured it at the end in Kelvin. As long as they're the same when you measure them, it doesn't matter which unit you're using. And then joules, we talked about a second ago, that's the standard unit for heat or energy. Good, we're going to measure all our energy in the form of heat this chapter. There's a work factor, but you'll use it in physics, not in chem. So this is kind of a little caveat just for fun, and a little, and it's not terribly necessary, but energy is always transferred between samples. It always moves from a higher temperature to a lower temperature. So you're never cooling things down, you're never adding cold. There is no measurement of cold, it's always a measurement of heat, either being given off or taken in. And so it always moves from the higher temperature to lower temperature. So if you put a can of Coke into an ice chest, right, you're not cooling down the can of Coke, you are warming up the ice chest is the idea. So always hot moving to cold, never cold moving to hot. I mean, it's a technicality, but you should know that it's heat being transferred. There's no measure of cold, just like there's no measure of dark, right? We have luminums, we can measure the amount of light, but we don't have any unit for dark. There is no unit for cold, and so we measure everything in heat, either taking in heat or giving off heat. Everything, every substance, pure substance, has a specific heat, and this is a good definition for us. The specific heat is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius or Kelvin. So how much heat energy do we have to put in to get a gram of a substance to increase a degree? And so you'll see some of them as we work through these problems. Water has an extremely high specific heat of 4.18 joules per gram times Kelvin. There's that value we saw on the first slide, is equal to 1 calorie. So 4.18 joules per gram Kelvin. So that's how much energy it takes to increase the temperature of 1 gram, 1 degree Celsius or Kelvin for water. To compare, iron's specific heat is less than 1. So it takes a lot more energy to heat up water than it does to heat up iron. It's one of the reasons the Earth is such a habitable planet we can live on, is because we're surrounded by this water, and that water, when we're facing the sun, the water is absorbing a lot of heat, so the planet doesn't heat up that much. And when we're facing away from the sun, it takes a whole lot of time for all that energy to leave the water, so we don't cool down that fast either. I don't know what the temperatures are on the sunny side of Mars and the dark side of Mars, but the temperature swing there is like 200 degrees from daytime to nighttime every day, and that would be inhospitable. Maybe that's a better word. So it'd be hard to live there because you'd have these massive temperature swings. So we're going to use specific heat in this formula where we can actually measure how much energy is taken in or given off by the mass of a substance based on its change in temperature. So Q is going to be the amount of heat, energy absorbed or released, usually in joules. M is our mass, usually in grams. We'll have to be careful with units, I'll show you in a second. C is the specific heat constant. Sometimes you see CP, because that's the specific heat constant at constant pressure. So anyway, it's not terribly important, but that if you see CP, that's why it's there. And then delta T is your change in temperature, Celsius or Kelvin. We're going to do a couple little calculations here on the next couple slides. So it's a good little equation. You'll use it some on the homework stuff that I'm going to give you. So here's a couple to look at. This says we have a 4 gram sample of glass, and it's heated from 274 to 314. It even does the subtraction for us. It says it was found to have absorbed 32 joules of energy as heat. What's the specific heat? So they are looking for here, what's the specific heat constant? What's that, CP? And so here is the first one. I'm going to do it right off to the side here. So this is going to be a Q equals MCAT problem. Generic equation's always good. I call it MCAT in AP Chem. Q equals MCAT. We are looking for the constant. So do we have the amount of heat in joules? We do. There's our heat in joules is 32 joules of heat. That's going to equal the mass of the sample. The mass of the sample here they gave us early on, and it said it's 4 grams worth of sample. We are solving for that constant, and they gave us the change in temperature. It doesn't matter whether the temperature's in Celsius or Kelvin. This one happens to be in Kelvin. That will make a little difference in the unit, but again, it doesn't matter whether it's Celsius or Kelvin. And so here we go, 32 joules divided by the 4, it's 8, divided by the 40, should be 1/5. And so we should get a specific heat constant. Should equal 0.2. The unit is joules over grams times Kelvin. That's our answer for that specific heat constant. Joules, there it is, divided by grams, divided by Kelvin, should be our specific heat. Hopefully that makes sense. And the second question says, how much energy is gained when heated from 314 to 344? So now they say, how much energy are we going to have to have released when we heat this thing, right? So how much energy will it gain when we heat it? So here it comes. Same Q equals MCAT. They gave us a change in temperature. We now have the constant of that glass. So this guy, we're going to solve for Q. Same kind of deal. Q equals MCAT. Set up the general equation. We're solving for Q this time, and we're off and running. It's the same piece of glass, so the mass is still 4 grams. We now have the specific heat constant, 0.2. That's joules over grams times Kelvin, times our change in temperature. We heated from 314 to 344, that's 30 Kelvin. And we can plug all those guys in. 4 times the 0.2 times the 30 should give us that Q is 24. Our unit here is joules because that's the unit on the specific heat. The heat gain was 24 joules. So that's how you do those Q equals MCAT problems. Like I said, you'll see a couple of them on your homework problems. See if I can get through a couple more slides here. So we have things called heat of reaction. This is in a chemical reaction. They show you how much heat is gained or released. They call this a thermochemical equation. So you can see this is a hydrogen reacting with oxygen to form water, except they've added a value in there. That value is the heat that is, in this case, released when hydrogen and oxygen react. Now we should look at this and go, that's a combustion reaction. So if it's a combustion reaction, then we should have some heat being given off, right? If we're exploding hydrogen, we should have heat given off when that water forms. And so this heat is given off as a product. It's called a thermochemical equation. We're going to see very soon that heat is given the letter H, delta H is what they'll call that. It's the change in heat energy. It's called enthalpy. This reaction, because heat's being given off, would be exothermic. And so our change in the heat energy, if we wrote it as delta H, would be a negative 483.6 kilojoules. That would be exothermic, this reaction, because heat is given off as a product. It's one of the products is there's extra heat. If you flip that equation over and we went from the water and turned it back into hydrogen and oxygen, then the heat required would be the same amount, except it wouldn't be given off. You would have to put that heat into that reaction. Forgive me, I cut the 0.6 off there. But that kilojoules here would be added to the water. So this thing would be endothermic. And the delta H, because you added the heat to the reactants, would be a positive 483. Good, we will pick back up there in the second PowerPoint. I only got 15 seconds before YouTube gets mad at me. So there's a good start to Thermochem. See you soon.